Yeah.
Yeah, I don't know if that's
It seems like you have like white spikes less black, so amazing great to put the screw out. That would be great.
there, that's better. Okay, let's have a look at one over here for lab 2. So lab 2, I want you to modify the STM32 Cube IDE project to use the blue button called B1 on the board and save the project as GPIO and regenerate your code. And we want to modify the program to cycle the RGB LEDs to RGB, and we're cycling through. And when the user button is pressed, it should just blink white. And it should blink at a 250 millisecond rate. The release, I said press or release of the button should continue the stepping of the LEDs in the correct order. So it goes RGB, and whenever you press a button, it's blinking white. When you let go, if it was on R, then it should be on G. If it was on G, it should be on B. If it was on B, it should go over to R. Okay, so it's constantly cycling and it knows where it was. So you blink white and then you continue on going where you were. Okay, so it's mainly getting familiar with the IDE and looking at some of the API to be able to go in and read a button and do something with that. If we go look over at the IDE, we have, it says B1 there in brackets. It doesn't, that's just for more information on the documentation, but it was called B1. I called my PB15 last time we were doing things red lead. Whatever you call it there, it's going to make a name, a port and a pin. So if I have red lead and then on PB14 I have green lead, and then on PB13 maybe I have blue lead. When you go, it's going to make the port all port B, GPIOB, and then it's going to make the pins 15, 14, and 13. And so one of the nice things about naming them is that in your code you reference them by the port, red lead GPIO port or red lead pin or what have you. And then if you need to change them around, it just defines in the main.h file to the new places, and all your code stays the same. Okay, so when I generated this, and usually if I went and did changes, you could go save and it should automatically generate. It will ask you if you want to generate the code, and it'll say, do you want me to remember that? And typically if you save it, you're wanting it to generate new code and go look. So all of these ones that keep saying, do you want to change perspective to debug perspective? Do you want to change perspective to looking at the C code? Yeah, you want to change the perspective. It's wanting to make sure, but you can click, don't ask me again, just whenever I'm going to the different perspectives to show it. So if it didn't save and you did make changes and it doesn't happen to recognize it, this little gear here says generate the code. So I can do that and it'll automatically go through and generate the code. Saving should kick this in and do that as well. Oh wow, that shows off the code very nicely on the projector, doesn't it? Okay. In here, we talked about it last time, there's a whole bunch of comments, /* and then some comments, //, and there's a begin and an end, and you have to put your things between the begin and ends. If you didn't, as long as you never went back to the IOC configuration file and regenerated new code, you're good. But the moment you change anything and generate new code, it keeps all the stuff between the begin and ends and wipes out everything else. It's its generated code. So you have to make sure that you're between those places. And sometimes I screw it up in if here in my while one, if I don't, I quite frequently will put it between the user code and while and begin 3 because that looked like a normal spot to put it. But it has to be above that. The user code begin while and end while is here, and then they have another set down here. So you have to look for the begin and ends, and it should keep your code if you go and change it around. So I should be able to go back to the IOC file, add another port, go and generate, and there it is. Now, one of the things I said was what it is doing. If we go down here and I look at main.h, so if I go to main.h and I right-click it and I go open the declaration, it should open up the main.h file. And so the main.h file says automatically we'll stick these in preprocessor directives that says, for instance, if not defined, __ main _h, because the file is called main.h, and the convention is to have whatever your name of your file is with __, all capitals, the name of whatever your file is, underscore, and the h for the header file. So it's saying if you haven't defined it before, then define it now. And what putting things by having these preprocessor directives in your header files, it means that if you needed main.h in multiple places, whatever one was called in first says I exist, and it defines __ main _h, and then when it needs it in another file, you say include main.h somewhere else. If it exists already, it doesn't bring it in again. And what can happen if you just said, I just want a .h file and I don't want any of this stuff, you can come up with multiply defined definitions or multiply defined variables or what have you, because you had main.h's in more than one file. So in this case, it doesn't matter which one was brought in first. It says there's this tag called __ main.h, and that's defined. So if you see main.h in another file, we're already defined. You don't get multiply defined things. Okay. The next line is if def __ C++. It's kind of grayed out, greened out, whatever. And that's saying, hey, if we were calling this is a C file, if we are calling it from C++, notify the compiler this is C code, use the C compiler, not the C++ compiler, so things work. It is grayed out because we are using C right now. We can write C++. I will talk to you about it. We are going to use C++ in combination with C. The IOC generation stuff is all C. Anything to do with the TFT and the graphics is all C++. And we'll link them all together. It happily used to not do it at all well. It does it fairly well now, and we will deal with that when it comes up. But it's greened out, grayed out, because it's not being used right now. Any of these preprocessor directives, I can make one and I can say, if def TFT, or you might have an if def debug or something, and include or exclude code. I'll often put in what type of TFT I'm using and link in the code for the different initialization for different LCDs. And so depending on what I have. So I will put into the properties in some of the settings just a name. I'll call it ILI 9341 for the display that you have. I might have different displays, and I want to have all the code in one and just say what LCD I have and link in the appropriate initialization files. Okay? Includes in here in main.h is STM32F4XXX HAL.h, hardware abstraction layer. Okay, so that's your API. The 1,800 pages of the API is saying, hey, recognize what some of those things are. So that's all in there. And so it's got a bunch of places we can put it. But way down here is what I wanted to see, all your private defines. That's all the stuff you named. Well, I named one of my LEDs red lead, and you have red lead pin. Well, what is it actually equal to? It's GPIO pin 15. It was on that. So I could call it GPIO pin 15, but that doesn't really abstract it. If I need to move it, I got to go through my code and say, where is it now? Yep.
Can you just manually go into the private defines and set up all your pins that way too? I know it's easier to do it on the actual like screen, but like will it let you type stuff in there?
Oh, it will let you type stuff and recompile. So if you just want to do something, so what I found, if you do something like that, then and it's good for a quick little check. But then when you go do something, your graphical environment isn't kept up with it, and if you make any changes, it wipes this out. It's not between its code. It's not between the user begin, user ends, right? So this you can do it, and I can say, oh, it wasn't on 15, it was on 14. Put 14 there, recompile, it all works, and then 2 days later, I go and hit recompile because I added something else, and all of a sudden my lights aren't blinking anymore, and I don't know why because I didn't do it through the generation. But you look, red LED says it is GPIO port GPIOB. So I could use GPIOB for the port, but once again, if I go red LED and then I move it over to port A, just recompile, it just changes the defines. All my code's still talking about red LED, and we just remapped it over. But this is if you're kind of going, where is this thing, or what, I'm getting an error and I don't kind of know why, you can go into main.h and see what it actually called it, And so, but I should be able to go red LED and go control space and pull up that IntelliSense, and it'll say, hey, red LED, I find pin and GPIO port. Which one do you want? Okay, and so you can go through kind of those. Some of the other things in here, so it put in a whole bunch of includes for the system, and the hardware extraction layer calls a bunch of the Cortex microcontroller interface standard APIs as well. And so this is more abstracted than the CMSys stuff. There's even what are called low-level drivers, and the HAL documentation will show you some of that. If you were optimizing your code and found something was taking too long, you can get closer to actually twiddling the individual registers. You can also just go and talk to the registers and access them yourself, and we will look at that too if you want to do that. But there are low-level drivers, and they start LL something, and that's to say, I don't want any of the abstractions. I am not going to make it portable across families. I just want to do something a little quicker to this A to D converter, or to this timer, or to this SPI module, or what have you. You have the ability to do all of that. Okay, and so that was in our main.h. Then if I go and highlight that, it was a serial port. UART2 was there, and it says it's a UART handle type def, and if I highlight over it, it's just a structure. All of these things, we're going to look more in detail at the GPIO structure. It sets up it has defines for structures for all of the different things that you need to interface with. You make an instance of the structure, you fill in the structure, you call the initialization function. It sets most of that up for you. We will go look at one in particular for the GPIO ports, and then we'll assume everything else is done. And again, we have system clock config, and system clock config will do all the stuff that is over here under clock configuration, and so that's all the different clocks that you look at. And so I think by default the board was running at 80 megahertz or something. It said 180 megahertz max, so I moved that over. If I want the low speed oscillator, that's for the real-time clock. That is currently not turned on, but there is a 32768 megahertz crystal, or you can use internal 32 for keeping track of time. The external, it says by default, it thinks that the board that it has is 8 megahertz. There's currently not a crystal stuck on here, but you can have anywhere from a 4 to 26 megahertz crystal. You'll get some boards that'll have 25 megahertz crystal. You get other boards that'll have an 8 megahertz crystal from different systems. If you have a board with a crystal, you can say, you know what, I don't want to use the internal 16 meg RC oscillator, which if you were using for some different timing and things may not be as accurate enough as an external crystal. You could hook up an external crystal. There is a pad on your board for that, but it's not there. So currently we're going through the high-speed internal. There's a bunch of phase lock loops that are getting turned on and to be able to give us the 180 megahertz. And then over on the side, it talks about APB2, APB1, all of these kind of things, and they go to different buses, and we'll talk about all of those. But all the configuration that's done here is over in main.c where it called system clock config, and it's way after main. Here we do the first thing from main, we do a hardware abstraction layer init, then it calls a system clock config, and then it's going to initialize your GPIOs, and then that UART, and then forever here. We were on here, what was I doing? I was just turning the light on, waiting 200 milliseconds, turning the light on, so that doesn't do too much. I could look at the toggle LED or something like that. System clock, here, these, if you highlight that, we talked about it last day, are macros to be able to enable the clocks for the certain buses, and I will talk about all of those coming up. And then here's the RC structure, and some of the things you can look at, it says PLLM 80, PLLN 180, all of, man, there's a whole bunch of stuff in here. And so it sets up all the individual things for the structure, and then it says, okay, how RCC OS config is the function to go off and do that. And if I highlight some of those, it talks about it and gives you the different parameters and all of that kind of thing for setting that up. Basically, this is going to take this structure and fill in all the ones and zeros. But you see, M is 8, N is 180. If we go here, M is 8, you know, and there N is 180. So it's just taking all the information from here and putting it into something that it can actually go and compile into ones and zeros. This is setting up then also for all the different buses and things as well. So here it says CPU, the advanced high-speed bus, the advanced peripheral bus, it's setting up all the clocks. We'll get into some of that kind of stuff. Setting up a UART, just by looking, by default, that UART was set. Some of the parameters, it's set for 115.2, 8 bits, you know, kind of thing. And again, that's going over here. And if I go to the pinout, and I go to connectivity, and it was UART2, and you see UART2 is there. It's set up for asynchronous, so it's just standard UART, a standard serial port. It doesn't have any flow control. If I zoom in on here, it says 115, 8 bits, no parity, 1 stop bit. So that's a pretty standard way, but I could change the baud rate if I want. You could do, if you were talking to something a little bit more unconventional, you could have 7 data bits, a 1 stop bit, 1.5 stop bit. It'll do all of that kind of thing. But just by default, you'll get over there. But sometimes you'll want to talk to things that are at a different baud rate. Okay. The reason this one is set up here is because in hardware, these two are set up to talk to the ST-Link, and will give you a virtual COM port as well as your ST-Link. So I have my ST-Link plugged in, I can debug code, and at the same time, if I use a command to send data out to UART, it's currently set for 115.2, I could have TerraTerm or something set up and be sending data to that serial port. And so it's just a HAL UART transmit, and you could send some data out. And so because it's got this virtual COM port set up, aids in some of the different debugging features and things that it's got that there. Okay, so we've got that. GPIO init, we'll look a little bit more in detail at this section. And so when I set up some of the GPIO ports, it's saying, okay, there is a structure called GPIO init type def. And the instance that they called it was GPIO init struct. It's currently got nothing in it. We turn on the clocks for all the different ports, and we'll have to look at a map to see where all of this is. But we turn on a bunch of bus clocks. And then it says, hey, write pin LD2. So that is my LED that was on board, and started off low. And then we have a red LED, and it says started off low. And you can select that when you go to the ports over here. And if I went over to the red LED, I say, okay, well, I set it as an output and I gave it a name. But if I come over here and I go to System Core and I go to GPIO, then look at PB15. Let's zoom over here a little bit. And it says it's low. Maybe I want it to be high. Or maybe I want it to be open drain. Or maybe I want it to have a pull up or a pull down. The other thing it has here is something says low, medium, or very high speed. I can have the clocks. I can have higher speed clocks and clock the data in faster if I have rapidly changing information. But if I have a push button or I have an LED, something that is relatively slow, and the default it'll just say, hey, low speed. But if you had rapidly changing data, you may say, this is in a separate place, and I need the data to get to the CPU quicker. I may want to see the changes. And the more you do that, the more power it takes up. And the whole ARM design, I could have it in my watch or what have you. You wanted to take up as little power as possible. It gives you the ability to change that. But that's some of the things. By default, it's just going to say, oh, it's low, and for a push button and a LED and things, we don't have to worry about it. But if you had higher speed data coming in, you may need to adjust some of these things. And typically that goes up to 100 megahertz, I can't remember, 50, 25, that kind of thing. Yep.
So with the GPIO output level,
yep.
Is that effectively changing whether it's active high or active low?
Yeah, this output level, when I go and initialize it, when it first becomes an output, do you want, because it sets the levels, then it puts it from default, it fires up, everything's an input, it will put it as an output. So when you first become an output, instead of high impedance when you're first booting up and run that GPIO init, do you want the level to start high or start low? The other thing that can sometimes be used here is do you want it open drain or push pull? So push pull's got the transistor to the VCC, and so if you want that not there, then you could have it open drain. So typical use for something like that might be you're trying to connect something up that's at a different voltage level, and as long as your current requirements are meeting, you could open drain and use an external pull-up resistor, for instance, to talk to a different voltage level. Okay, so you can do things. In general, it's you want it just the output to be push-pull. And then we've got our user label. So I can go in and configure all of that. All of that will show up over here in some of your structure. So before putting them inputs or inputs default is going to fire up as high impedance inputs. We set or clear the output levels, and then we fill in the structure. Now we had the GPIO init type def, and the instance was GPIO init structure. If I highlight over that, you'll see it's GPIO pins to be configured, mode, pull, speed, all of that kind of thing. And so if I look over here, GPIO init struct, and then if I just type GPIO init struct, for instance, and you do that, and then I just go dot, it's going to say, what in the structure do you want? There's alternate, there's mode, there's pin, pull up, pull down, speed, which is all those things graphically I saw. Yes?
If you were to set the where it was pull up and pull down resistor, does that actually eliminate the need for the resistor, or are you just setting what you fired out?
Oh, no, so here, if I want a bunch of switches, yeah, and I just want pull-ups, you can do it here. Yeah. Yeah, so that's one night. You could say, okay, it's only whatever, a quarter penny a resistor, but if I have a million boards times a quarter penny and I just did this, then I've saved money. Okay. So we have, as far as pin, we have the mode for push, pull, open, drain, pull up, pull down, the speed at which we go. And then the very last line, so this init struct, we fill in the structure, and then we type in how GPIO init. So this structure is set to work on any of the ports, but it doesn't know what port. Okay, and so I have an instance of this structure. I fill in what pins I want to work on, whether it's one pin or all the pins on a port. I then set up the modes. I set up whether it's pull up, pull downs. I set up the speed, and then HAL GPIO init, I say, hey, this structure, work on this port. And I can't remember if I went there and looked at what it was in main.h, what port it's on, right? That was in main.h. And then the address of where this instance of this structure is. So this structure was defined here. Fill it in for B1, call the initialization, then refill in the structure, call it for LD2, because this thing is a button, and it's going to be on this happens to be on an interrupt. This is on an LED, so it's going to be an output push-pull. And then we have red LED, and it's on another port. And so this is, I don't remember what port it's on, port A maybe, and this is on my port B, pin 15, and so we set it up for the individual one. So here's a structure, call this function, pass it the address of the port that you want it to work on, and here's the address of where the structure is. This function goes and looks at what the data is in the structure and applies that information to the registers at that port. Okay, and so we'll have to have just a little look at where that's going. And so here, not here, where is it? Okay, this is in the week 2 information, and so this information, we see that it's in the main.c, but if I go and look at, remember I said there was the STM32F4 HAL GPIO, which has got all the information from the HAL API. If I go and search on that, there is the GPIO init structure, and we highlighted and brought it down. So here's it just copied over. And so we have like pin, mode, pole, speed, alternate, and pin. It says specifies the GPIO pins to be configured. So if I configure my red LED pin and my green LED pin and my blue LED pin, and they're all on the same port, what it will do is I can put in red LED pin or green LED pin or blue LED pin, and it's just looking at a 32-bit number for what pins on that port. Now the port is 16 bits, the thing is 32 bits, and we'll look at that in a minute. The ARM is a 32-bit processor. We're dealing with things in 32-bit. And so mode, again, is a 32-bit register, and we want to look, and it says specifies the operating mode. This parameter can be part of the GPIO pin mode defined, and we'll have a look at it. So here's the structure, and we made an instance of it. I just copied and pasted that out of main.c. We just looked at it. If I had 3 pins, I call the pins RGB_B, RGB_G, RGB_OR, and the pins are defined as these. And this is probably, this could be pin 15, pin 14, pin 13. So you look at a 32-bit number, and this is going to be the bit 15, maybe bit 14, bit 13 in it. Okay, and so it just ORed them all together. So on my 32-bit number, it pins at bit position 15, 14, and 13, they're ones. This is just telling, when I do HAL GPIO init, it goes up here and it says, what pins on that port do you want me to set this stuff up on? And it will set it all up. Okay? So again, in this one, I put them on pin 7, 8, and 9 of port B. Here are the pin definitions. So if you actually go and look for what they are, they're saying, okay, well, this is just bit 1, the second bit, the third bit over, the fourth, fifth, sixth, all the way down. And then they also have an all pins, GPIO pin all, sets are 32 bits as all ones. Okay? Or 16 bits, sorry, as all ones. Okay? And so when I go GPIO pin 1, I could just put in a 2 or 0B 0000010, you know, what have you. But they put those all in the defines. So this is in one of the manuals that actually shows you the pins. So the very first thing over here, we were saying pin and then we were saying mode. So pin says, what pins do you want me to work on? Mode says, okay, it says address offset 0, GPIO-X mode register, GPIO-X where X is A through H. So the same thing for all the different ports. GPIO-A port, GPIO-B, what port do you want to work on? And so it's a 32-bit register. We looked at that, seeing that it was a 32-bit register. Each register is read-write, and it says down at the bottom here, it says, here's the different things I can do for my mode. So I can say, by default, inputs. So when the ARM processor fires up, the ports are all inputs. That's the reset state. I can be general purpose mode, analog function mode, alternate function mode or analog mode. Alternate function mode, I might have SPI, I2C, maybe a timer output, something else, an A to D, something other than general purpose I/O. So we could set it up for that. So when you set it up for, one of these other things, it may not be just a general purpose I/O. If you want it as GPIO, it's either going to be a 00 or a 01. So when I say in the drop-down menu, you're an input or you're an output, it needs to set up for the first pin. Bit 0, it needs to set 2 bits. I'm either a 00 for an input, that's the default, or a 01 for an output, or a 10 because I'm a SPI port or something like that, or a 11 for analog mode. Maybe there's a comparator or something on there for that. So by setting up that the drop down that I wanted, input, output, what have you, when you call a HAL GPIO init, it looks at what port you're on, and the offset to this port is 0. So whatever address in memory port B is, it is going there and then looking to see if you want input, output, or whatever, and changing the bits here. Okay? If I then was on, wanted to do something, and this was port B, and I wanted to do something on port A, it would go to the base address of wherever port A is, and at the offset of 0, don't go any farther, just be at the very first 32-bit word you're going to see, the very first 4 bytes, you're going to see this, and you change them with 0, 1, 1, 0, what have you. Before the Cube IDE did this for us, you had to go do this. You had to go look, and you had to put the 1s and 0s in the registers. I am showing you the registers, showing you this is what happens with that GPIO port, and it does it all for us. Yeah.
So all those registers are just to set up those 4 things like input, general purpose.
Yeah.
And that's all 30.
That just does input or output, alternate function. The speed and all of that is more. All of that has to be done before a light blinks. Yeah.
If you try to write to an extra register, does it erase or overwrite the first one, or does it return an error?
Yeah. There's if we look at some of the code, there are checks to see if you have put things that are out of bounds in most cases, and it will go, I don't know what pin 32 is because it goes from 0 to 31. But it won't wrap around or do anything like that. If anything, it will truncate and you just get whatever you had there. But a lot of the code has these directives in the functions to say, did you ask for 16 bits on a port? Did you ask for, just 32 bits? So it is pretty good at some of that. So in here, I said the mode is output, push, pull, and over on this one, output type. And so the offset is 4. The other offset was 0. Now, why is the offset 4? This offset was 0.
So we could look at the 4th
Yeah. So we're at a base address somewhere, wherever port B is. Don't know where it is. Okay, it's somewhere in memory. I'll show you where it is. Okay, so wherever port B is, let's say it's at 20 million. Then 20 million and 0 is right here. 20 million and 4 is the next register because we just used 32 bits, 4 bytes for this. So it goes to 20 million, goes to 0, then it goes to 20 million and 4, does the next 4. So sitting at port B, 4 bytes away, because we just used 4 bytes for this one, is this one. And it's setting up for your type. And the type is push-pull. That's the default, so don't do anything, and it's going to do that. And then open drain. And so it only needed 16 bits to be able to figure this out. It has, to keep everything 32-bit, it has reserved the upper bits, so it's not using those. So I have the choice of either just 1 bit. It's either output push-pull or output open drain. So I'll put a 1 or a 0 in all here. That GPIO init goes and does the first 4 bytes for that first one. Then for the output type, it goes 4 bytes over, and it's going to say the lower 16 bits. It's going to put one or the other in for the port, and that's it on the HAL init.
Oh,
And
question.
Yep.
For the output open drain, is that just like it's on like all the time? Is that what that means?
Open drain just removes the essentially the ability to get a high out of the output. So if I set something up and you are put an LED on the thing, and so I want it to go high and low, or just a logic probe and you want it to go high and low, it will go low and nothing. And so it's relying on you putting an external pull-up resistor. And so some bus systems, for instance, will have a common pull-up resistor and then use lows to be able to determine something. Or, like I say, another way is, as long as the current requirements were okay, you could hook it up to a different voltage level. And then, so everything else is hooked. This is 3.3 volts, and you might have something hooked up to 5 volts. Okay? Yeah.
So what they're saying here is that like all of the first 16 bits need to be 0 to be a push-pull.
Yes.
Okay.
All of them need to be 0, and that's when you don't talk to it, you first power it up, it has set that up. So but when you go into the graphical system and do it, it fully fills in your structure, your GPIO init structure. So that was 32 bits, so that means we're now at offset 8. And at offset 8, it says speed register. And my choices for speed register, this is all in week 2 data sheet info, by the way. And so it says here, now there are some, depending on what else is on them, there are reset values. By default, the reset value is low speed, but there are some differences depending on what port and what else is there. Okay, so if there was something going on a certain port, you might go, oh, the reset value I thought was going to be low speed, but it's not for in one place. You can see they're not all necessarily 0 zeros. Other ports other than A and B are. But here's my choices on this. I have low speed, medium speed, fast speed, and high speed. The old data sheets used to say, and I can't remember, it was like that was 100, that was 50, that was 25, and that was 10 or, no, 2, I think. And so now they just reference, you have to go look in the manuals to see more detail about what your actual speeds are. So again, for our speeds, so because I have 4 options, I have 2 bits for each. So it's a 16-bit port, but I needed 32 bits because there's 2 bits to configure each port for the speeds. Default, when you just use the graphical environment, it's just going to set up low speed, and then it's up to you if you go, I have a high speed thing and I'm not getting the information or I'm missing some bits, you can change that around. Okay, so we are at the base address, and we now went at an offset of 8 to be able to go to that one. And then let's have a look at the pull up, pull down. And again, we have 2 bits. It's either no pull up and no pull down, and that's going to be our default for most. or a pull up or a pull down. So if you had need for a pull up resistor to make sure that some chip that you had was enabled or disabled when you were fired up, when you first initialized things, you can put that in without having to have those extra bits. You can individually on most pins set those up. And again, because there's, well, one option is they don't know what other kind of thing to do it, but to keep it there, we have either 000110. 11 is don't do that. Who knows what it'll do? So when we put it all together, we have our MX GPIO init, which is called, which when we scroll down in the main.c file, we have this GPIO init struct, which was cleared, and it was just an instance of GPIO init type def. And again, highlighting our mouse over it will bring it up. The HAL RCC is just turning on the clocks for port B. The ARM chip is up here, the ports are down here, and it's just turn on the clocks for the bus to move data from one to the other. I will show you all of that coming up. On this one, I had GPIO-B, and it was RGB-B, RGB-G, RGB-R. I didn't call it B, but it knows this one's on B, and this one's on B, and this one's on B. If I just had one, it would call it RGB-B port. But because it didn't know to call it B port or G port or R port, it just said, well, you're all B, I'll make it B. Okay. But this is part of filling this in, is saying there's a 1 here, a 1 here, a 1 here. These pins, I want you to do this stuff too. And this is the function that goes and does. Okay. All of them kind of work like that. We just talked a little bit about this one in particular, how it works. There are a couple other things, and I will show you. The simulator is great at showing this and where all these registers are, and you can actually step through the code and look at the bits of the registers all change, and we'll look at some of that. You set up an input, or you will set up an input to read a pin from the button, or you set out an output to send data out to the LEDs. So if I look at that, that's address offset 0x10. So there's the base address for port B, port A, port whatever, and then there was all those offsets to set things up. Then there's also input registers and output registers that are associated with it. And so it says the input port, it says it's read-only. Makes sense, it's an input port. I probably shouldn't be writing to it. And it says bits 15 to 0. These bits are read-only and can be accessed in word mode only. They contain the input value of the port. In other words, I can't just read the individual bit. I have to read the whole word to get all the information from the port at once. It's a 16-bit port, so even though we have 32-bit registers to make the offsets all work, we only use 16 bits of it. And so we can actually go into the with the IDE and step through code and actually go to the register and see what bits are being actually read in. 4 bytes from that, because they were all 32-bit words. There's the output data register. So the output register, I can read and write it, because you do a read, modify, write. If I wanted to add something to it, I read the value in, I write it back out, for instance. And so output, it's again 0 to 15. They can be read and written to by software. And so when I use the GPIO B underscore output data register, I can directly write to the port as long as it was initialized. You have to set it up for inputs, outputs, do that whole thing. I could directly write to that register. I could go to the GPIO B output data register and write a value and send the data out. Okay. It does say for atomic bit set reset, the output data register can individually be set and reset by writing to the BSRR register. I have no idea what that means. Let me go to main.c. Where did I write something? Way over in my one. Let's go there. The actual code, Wow, does that not show up well on the projector?
This light too, maybe?
Maybe. Wow, it's awful.
Yeah, that's bad.
Well, I even put I put the fonts larger and things. You were asking about pins. There's an assert parameter, that's a preprocessor directive. It's saying, is GPIO pin a valid pin? So it's trying to see if I was a 16-bit port and you were writing the pin 18 or something, it goes, you can't do that. So it should give you an error to say, yeah, I don't like this. So a lot of them have that. But one of the things I wanted to point out is this is how GPIO write. That's what you all used last day. And when we go and look at what's in there, it checks to see that it's a valid pin. And then it says, hey, if the pin state is not equal to reset, then we're going to go to GPIO X, whatever parameter X was, be bit set reset register is equal to the pin. Okay? And so it's going to take GPIO X, port A, B, C, red pin port, whatever, red port, or what have you, and it's going to then use the bit set reset register, okay? And so then we have the pin and the pin state and things. So it's using the bit set reset register, not the output data register. Right pin uses this one. Well, let me just go back to that document again, wherever it is. Microsoft has decided that it's going to read my PDFs for me, so it's kind of throwing me off a little bit here. Okay, so there was the output data register, okay, but it says for a so we can use that, and we can go to GPIO B output data register, directly put in 16 bits, and it'll, as long as they were all outputs, you're going to write it out. But it's saying, hey, for atomic bit set output, output data register can individually be set. This is this port, which is again at 18 off the base of the registers. Okay, and so here is this one. And so what it means by atomic is I want it to go all in one motion. I don't want you to do a read, modify, write, and somewhere in between get an interrupt, go somewhere, and kind of lose track, didn't complete the write. So this is non-interruptible. It's all going to happen at one go. Okay, and so how GPIO write does this, sets or clears the bits. So it's a 32-bit register, 16-bit port. So it says, okay, bits 31 to 16, these bits are write only and can be accessed in word, half word, or byte mode. So I can look at just a byte or do the lower 16 bits or do the whole 32-bit word. No action on the corresponding output data register bit, so don't do anything. 1 resets the bit. So 31 to 16, in 0 to 15, if I put a 1 there, it puts a 0 in the bit. 1 resets the bit, 0 does nothing. In 31 to 16, so up there. 0 to 15, if I put a 1 there, it sets the bit. So if I want to set bits on the 16-bit port, if I go 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, all the bits are high. The port is all high. If I want to clear the bits, I put 1s in the upper 16 bits. That clears them. So this sets them, that clears them. Writing 1s. Writing 0 does nothing. And then it's like, okay, any problems with that? Everybody's good with it? So if I write a 32-bit register, I'm going to write it. If I put a 1 here, I set it. If I put a 1 here, I clear it. Yep.
You can write 1s to, like, for example, both 0 and 16.
Yeah. So what happens if you write 1s to all of them? Does it set it or does it clear it?
Whatever it does last.
That's potentially.
Or race condition, and it just says random.
Where is it here?
So when you want to set them, what would you write?
You don't want. Oh, there it is. Okay, right there. There's the note. I knew it was somewhere. If both set and reset are set, because you set the reset to clear. Anyway, if both set and reset are set, the bit set has priority. So if I wrote all ones, you get all ones. It says bit set has priority. So this is bit set, this is bit reset. If I write ones there, it'll clear. If I write ones there, it'll set. Write them all. It says that this one takes over. But it could be undefined, and you could get some that are there. So that is in week 2's GPIO configuration port. And typically you would go through and look at these individual registers, and we used to have to do that. It does it automatically. It was below main. It's called GPIO init. Anything we look at after that, we're going to look at the API and assume that if you need to go look at it, it does this stuff in the background. Okay? We'll leave it there. Thank you.
Thank you, Mel. It's all numbers there. So, one time.